One end of a light inextensible string of length 2 meters is attached to a fixed point O. A particle P of mass 0.2 kilograms is attached to the other end of the string. P is held at rest with the string taut so that OP makes an angle of 0.15 radians with the downward vertical. P is released and t seconds afterwards OP makes an angle of theta radians with the downward vertical. Show that d squared theta over dt squared is equal to minus 4.9 sine theta, and give a reason why the motion is approximately simple harmonic. Here is the particle theta, and here is the gravitational force. This is theta 2. This side and this side is equal. It's opposite, so it's m times g times sine theta, and we use Newton's second law transversely. This is the force, and this is alpha, angular acceleration. It's second derivative of theta. We can divide m, we get this equation, and divide 2, we get this equation, and we know that for small theta, sine theta is equal to theta. Now, for example, we can calculate that sine 0.15 is equal to sine 0.149. We can apply this equation, so we get we can write here theta, and this equation represents simple harmonic motion. Using the simple harmonic approximation, obtain an expression for theta in terms of t, and hence find the values of t at the first and second occasions when theta is equal to negative 0.1. Let's see. Simple harmonic motion is when net force is equal to minus k times x. K is a constant, and we know that net force is equal to m times a. A is equal to second derivative of x. We divide m, and we get this equation. We can use this mark. Omega squared is equal to k over m, so omega is equal to square root of k over m. This is a differential equation, and its solution is this equation, and velocity is equal to this, and acceleration this. Phi phase, omega angular frequency, it's important, not angular velocity. Here it is angular frequency, and A is amplitude. We use this. Here is an analogy. Now we have this equation, and if we compare these two equations, we can see that omega is equal to square root of 4.9, and theta is equal to this equation, and we know this initial values, and if we write this here, and A is here, and T0, we get that phi, the phase, is equal to 0. So we have an expression for theta in terms of t. Now we know that theta is equal to minus 0.1. We get t first and t second. We write this value here, divide 0.15 and change the sides. We get this equation. This is a trigonometric equation. We see that some cosine is equal to a negative value. We know that cosine is negative in the second and third quarter. First we calculate a temp value. We should calculate with calculators. We should change degree to radians, and second function cosine 0.667. This is very important, not minus 0.667, 0.667. We get this value, so this is a temp value, and in the second quarter the rule is that p minus x0, so this value is equal to p minus x0. So we get the first time, and in the third quarter the rule is this angle is equal to p plus x0. So we get t sub 2 is equal to 1.8 seconds. Find the angular speed of OP and the linear speed of P when t is equal to 0.5. We'll use this formula. It is here, not x instead of theta, and substitute phase was 0, omega A and we get this value. Very important that we should change our calculator to radian instead of degree. So this is the angular speed, and linear speed is equal to r times omega. It's 2, so we get the linear speed.